So this video will be about showing the general procedure about how to find the singular value decomposition of a 3x3 matrix. I wanted to do a particular example, but I was unable to find a matrix where the eigenvalues, and so the eigenvectors, the u sub I and v sub I, are simple. I mean, no complicated number. Yeah. So unfortunately, I won't do a precise example, but just the general procedure. Yeah, so if you think this video is useless, then don't watch it. Yes. Yes, so if I have a 3x3 matrix A, and I want to do a singular value decomposition of it, so remember the first thing you do is you find A times A transpose or A transpose A. Here, if you have a 3x3 matrix, it doesn't matter if you take A times A transpose or A transpose A. Remember that in the last two videos, if you had a 3x2 matrix or a 2x3 matrix, it could make things simpler if you take A times A transpose or A transpose A, because in some cases you get the 2x2 matrix and in the other one's a 3x3 matrix. And so it's simpler to find the eigenvalues. But here it's not the case. So yeah, you are free to choose between A times A transpose and A transpose A. Then you find the eigenvalues, lambda sub I of this A times A transpose or A transpose A, and then you find the associated eigenvectors of A times A transpose, respectively A transpose A, by remembering that the eigenvectors of A times A transpose will give you your u sub i's, and the eigenvectors of A transpose A will give you your v sub i's, where the u sub i's are the vectors inside the matrix U, and the v sub i's are the vectors inside your matrix V. Remember that you need to normalize your vectors v sub I and u sub i's, and yeah, that at the end, I mean, the vectors will be orthogonal to each other. Because remember that U and V are orthonormal matrices. That means that the vectors inside I are orthogonal to each other, and all vectors are of length 1. Yes, and then you can also find your singular values. Remember that the sigma sub i's, I mean the singular values, are equal to the square root of your eigenvalues. So sigma sub I is equal to the square root of lambda sub I. And also remember that A transpose A and A times A transpose have the same non-zero eigenvalues. So if lambda is not equal to 0, for A transpose A, for example, then A times A transpose will have the same eigenvalue too. But this is also only for non-zero eigenvalues. Yes. But I think you should know that by now, if you have watched the previous videos. Yes, and so once you have found your u sub i's, respectively v sub i's, you can either compute the other matrix that you didn't compute. So if you computed first A times A transpose and found the eigenvalues and then the u sub i's, you could now compute A transpose A and find your v sub i's. Or you can use the shortcut methods. If you remember, v sub I is equal to 1 over sigma I times A transpose times u sub I, and u sub I is equal to 1 over sigma I times A times v sub I. Yes. And remember that this only works, of course, if the sigma, so the singular values, are non-zero, so if the eigenvalues are non-zero. So if you happen to have a third eigenvalue, respectively a singular value that is 0, here we are in 3 dimensions, so we can simply use the cross product to find our third vector. Because remember that, I mean, at the end we just want vectors that are normalized for our matrices U and V, and that are orthogonal to each other. So in 3 dimensions, you can simply use the cross product. If you have already found our first vector U sub 1, U sub 2, respectively V sub 1, V sub 2, depending on which matrix you computed first. I mean, A times A transpose or A transpose A. And yeah, so if you found the first 2 vectors, if you're in 3 dimensions, you can simply use the cross product to find the third vector, u sub 3, respectively v sub 3, which will be orthogonal to the 2 others. And then you simply need to normalize it again. Don't forget the normalization. Also, for those formulas, it may happen, it happens generally that if you find your u sub i's, and you use those formulas to find the v sub i's, that your v sub I, you need to normalize it again. And the same thing for the u sub i's. If you have found your v sub i's and use those formulas, you need eventually to normalize your u sub I here again, because it won't be normalized otherwise. Don't forget that. Yes. Yes, so now you have found your u sub i's and v sub i's, so you can plug them into your matrix u and v. So you the matrix u will have the vectors u sub 1, u sub 2, u sub 3, and the matrix v will have the vectors u sub 1, v sub 1, v sub 2, and v sub 3. And also remember that you have your matrix sigma, which contains the singular values that will be in the diagonal, and you will have 0 elsewhere. I mean, yeah, everywhere 0. And remember that the singular values, so which are equal to the square root of the eigenvalues, are ordered, need to be ordered from the biggest to the smallest one. So the first eigenvalue is greater than or equal to the second eigenvalue, which is greater than or equal to the third eigenvalue. Yes. Why we need to do that? I mean, there are several reasons, but the main reason I am aware of is that, like, if you use a singular value inside your computer, and that because of lack of storage or whatever, you don't have enough place, and you need to cut out a few singular values, you just cut out the last one, then the second last one, and so on. Because remember, if they are ordered from the biggest to the smallest one, you know that the smallest one, so the one that have the least influence on your system, yeah, are at the end. And the one that are the most important to your system, that have the biggest influence, are at the beginning. So you begin by cutting out the last one, then the second last one, and so on. That's the main reason I am aware of. You just know where the important values are at the beginning, and where the not important values are at the end. Yes, that's the main reason I am aware of. Yes, so don't forget to order them from the biggest to the smallest one. Yes, and so remember that if you have a m by n matrix A, where m is the number of rows and n of columns, your matrix U will be a m by m matrix, your matrix V will be a n by n matrix, and your matrix sigma will be a m by n matrix, so the same number of dimensions as A. And so if you are in 3 dimensions, if you have a 3 by 3 matrix, sorry, U will be a 3 by 3 matrix, V will be a 3 by 3 matrix, and sigma will also be a 3 by 3 matrix. So all matrices will have the same number of dimensions. Yes, and just remember the geometric intuition of the singular value decomposition. If you have A is equal to U sigma V transpose, you can write it as A V is equal to U sigma. Okay, because V is orthonormal, so its inverse is its transpose, so you can multiply by V on the side here, and this is simply the identity matrix. Yes, and now if you imagine that there is a vector x here, so this has nothing to do with the x here inside, it's just a vector x. You can call it whatever you want, y, whatever. Yes. What the singular value decomposition does basically is you imagine that you have a vector x in some basis, orthonormal basis, so it can be the default basis, like in 2 dimensions the vector x and the vector y, and in 3 dimensions the z component here. I mean, the z will be this one in 3 dimensions, the x will be this one, and the y will be this one. It can be that basis, it can be any other basis that's simply orthonormal, so the basis vector are orthogonal to each other and they are of length 1. So if this vector x is expressed in this basis V, and then you apply A on it, your matrix A does 2 things generally. I mean, it does only 2 things. It rotates your vector, and it stretches it by some amount. So like it may turn it by 90 degrees, I don't know, and then it may stretch it by a factor of 2, or by a factor of -1, I don't know, or 0.5, I don't know. And the singular value decomposition states simply that that transformation that A does on your vector in your basis V, we can express it as the same thing as if you have some other basis U that is also orthonormal, that will play the role of rotation. Basically, the rotation the matrix A does can be copied. I mean, yeah, can be done by the basis U. It will be kind of like the rotation, and the stretching factor of your matrix A can be done by the matrix sigma, which contain the singular values. And all that, of course, is applied to your vector x. So you have a vector x, you stretch it, so that will be the stretching factor. The sigma will do the stretching role of your matrix A, and then U will be the rotated basis, and so it will play the role of the rotation of your matrix A. Yes, that's what the singular value decomposition does, and that's also why why I said that the singular values are ordered from the biggest to the smallest one, because I mean it's the same thing here in the matrix sigma. The most important stretching factors will be used first, and then the least important stretching factors, like that the 17th component of your vector x is only stretched by 0.01, while the first one is stretched by I don't know 10,000. I mean, yeah, it's ordered like that to make things just simpler. That's the reason. I hope you understand what I mean. Yes. So here, I mean, it's a picture of what the intuition, the geometric intuition. Like you have your normal basis. Like here, it's the normal basis in 3 dimensions, so x, y, z, and you have your vector x. X here in red. And I mean, if you apply it, if you apply the matrix A to it, you have your vector that's now here. And we can simply say that instead of applying A, we can simply imagine that there is another basis, like here, like x prime, y prime, and z prime. So this rotated basis here, which will, as I said, rotate our vector x, and then we apply our matrix sigma to the stretching factor. That's just what we do. That's the intuition of the singular value decomposition. I hope you can make a bit of sense of that. That's as simple as that if you understand. If you understood it, of course. Well, if you don't understand, it's not simple, obviously. Yes. So yeah, that's the geometric intuition. I hope it was useful. So again, I couldn't find a matrix where the 3x3 matrix where the eigenvalues and eigenvectors are simple, and that's why I just did the general procedure. So yeah, maybe it was a useless video. I don't know. I still hope that you could learn something from it. Yes. Yes. Thanks for watching.